Mhm. Thanks, Eric. Thank you very much for inviting me to give a talk, and I'm very happy and excited to talk about our recent work. I understand that there are many math experts in like as the audience, so I hope this talk can give you like some application side of how we mathematical characterize score learning and diffusion model and how it can have some applications in real world diffusion models. And yeah, I hope you enjoy this talk. Yeah, and in this talk, I'm going to talk about our research paper when score nurse geometry, the rate separations under the manifold hypothesis. And this work has been accepted to iClear 2026. And this is a joint work with Dr. Zebang Shen, Dr. Yaping Xie, and Professor Niao He. And we are a group of people from ETH Zurich. So in this work, we concern about the sampling problem. We want to sample from an unknown distribution P data, given samples from P data. And a very usual way, common way to do this is to do score learning. That is, we learn a score function, basically the gradient of log P data. And then by some parameterized models like neural networks, and then we use this score to try to sample from P data. For example, plug it in the Langevin dynamics and run it long enough so that we can sample from P data. And this score learning has become the core component in modern diffusion models. So in diffusion model, we have P data as our initial distribution at time zero. And then we gradually inject noise to corrupt this real data to pure noise. And then in the reverse process, we use the nerd score function to gradually denoising, and then hope to recover the P data, the realistic images. So here the score function here is the key. So how well we can recover P data depends on how well we nerd this score function. So actually, the diffusion model makes more sense under the manifold hypothesis. So if we consider the support of P data is on a low-dimensional manifold, then directly learning a score function here is very hard because then we are looking at it from the ambient space, the Euclidean ambient space, and then the gradient becomes very singular. But however, in diffusion model, we add noise in the ambient space to this P data and make it to expand it in the ambient space to make it a distribution supported on the ambient space. And there we can actually be able to nerd the score function to well approximate this score function. So more specifically, we consider the variance exploding SDE, which is commonly used in diffusion model. That is, the drift term is zero. So we don't have the drift, but purely to add some noise. So I should note that our framework also applies to variance preserving SDE. That's also commonly considered in diffusion model. That is, for the drift, we consider an OU process. The drift is linear on X, such that the variance is preserved during the whole process. So now we're considering the case for simplicity that we don't have the drift and we simply add noise to it so that the variance can explode. And specifically, at some time t, if the injected noise has magnitude sigma, then the ground truth distribution P sigma is simply the P data convolved with a Gaussian with variance sigma squared. And the corresponding score function is the gradient of log P sigma. And the goal of diffusion model is to nerd as accurate as possible the ground truth score function and then use it in the reverse process, trying to recover P data as t goes to zero. So we can see that an important regime to consider in this process is as t goes to zero, as t goes to zero. That is when we are about to recover the P data, which also corresponds to here, the small sigma limit as sigma goes to zero. And in practice, there are like many problems regarding this regime. Like you cannot usually learn your score very well in this regime. So in practice, when sigma is very small, people often observe that the training loss even diverge. So you cannot obtain a very accurate score function using, say, training of your neural network when the sigma is very small. And in this framework, we're trying to give an explanation why. So even we cannot learn the score very well, we can still like generate realistic images. The diffusion model is still so successful. So we consider the manifold hypothesis that P data is supported on a smooth manifold M. And intuitively, you can consider that if the diffusion model is trained on realistic images, so the manifold is basically a set of all realistic images, right? And we try to do a fine-grained analysis of the score learning under this hypothesis. So first, let me go through some conventional stories about diffusion model that what people think about it in the past, and also about score learning, that people believe they try to use score learning to learn the distribution, the actual distribution. But however, the empirical evidence is usually very unclear because it's very hard to verify whether your generated data actually follows P data, right? To my knowledge, this little can be done to verify this. What people do is usually just, okay, I generated realistic images. So we compute some scores to some metric to verify whether this image is realistic enough. And then we try to generate diverse images as much as possible, right? And this also reflects that typically learning the distribution is not the goal of practitioners. So they are happy if you can generate, say, realistic cats, right? And make it very diverse. So we have, it's not simply memorizing the original data. Cool. And so our story is as follows. So we believe that in practice, score learning cannot learn the distribution, but actually learns the structure of the manifold, the data support manifold. So this partially explains why a diffusion model is so successful, that maybe it does not actually have the density well learned, but as long as it learns the structure, learns the manifold, you can already generate very realistic images, right? So here I'm going to present a meta theory that shows this idea and give an intuition on how we prove it, and then dive into our main theorems. So consider the arrow sigma as your score arrow, the arrow between your score and the ground truth score, the gradient of log P data convolved with a Gaussian. And then under the manifold hypothesis, we want to show that the distribution learning is much harder than manifold learning in terms of the score arrow. And another implication is that score learning must learn the manifold before the distribution. So we will see that in order to fully recover the distribution, you must have learned the manifold. So in diffusion model, it's actually they are implicitly learning the manifold before the distribution, although many people think we are directly targeting the distribution. So how do we show this? So we consider the manifold hypothesis, and then let's consider what is the log P density looks like, and the gradient of it is just the score function, right? And then this is the log density function is basically the log and the P data distribution on the manifold. So U here is a parameterization, the tangential coordinates of the manifold, and convolve with the Gaussian distribution on the ambient space. And then we do a expansion of this function with respect to sigma. So basically here, mathematically, we use the Laplace method approximation to approximate this integral. And then we find that the very leading term, the term of order 1 over sigma square, is purely a geometry term. So it's just the distance to the manifold. So here the expansion is expanded. So near the tubular neighborhood of the manifold. So here we have a unique projection onto the manifold. So the first term is just the distance to the manifold with no side information like the p data, the density information, no of that. So as we can see that as sigma goes to 0, this term becomes very dominating and very large. And it actually forces your density to concentrate on the manifold. Here's an illustration where the manifold is just a 1D circle embedded in the 2D space, the density function. And as sigma goes to 0, so points with density, points of the manifold will have density exponentially decay. So most of the mass just concentrates on the manifold. So this term tells us that so the leading term determines the support of the limiting density, which is the manifold M, the support of P data. And it's a pure geometry term, meaning it locally behaves the same for all use. It does not introduce any other like bias towards the distribution you recover. And then in the theta 1 term, in the higher order term, we see that it includes the original data distribution P data as some curvature term. So this implies that in order to recover your initial distribution P data, an error of order big O1 is unacceptable. If you have an error that's of that large, it can contaminate your P data and affect the term here. And then you cannot fully recover your density. So here's a nice plot that tells the rate separation here. So the x-axis is how bad we know the score function. And if we have the score to be very well known, so the small o1, so that we can recover P data, because here the two leading terms are very cleanly recovered. And then if we only know the score function roughly, that is O small o sigma to the -2, then we only recover the leading geometry term. That forces our distribution to be supported on the manifold. So we have, say, for instance, a realistic photos. But however, the density information is lost. So you can generate arbitrary distribution on this manifold. And of course, if we know the score even worse, then the support is even no longer on the manifold. We cannot recover a meaningful distribution on the manifold. So our main theory is developed as follows. So we compare the distribution learning with partial structure learning. So we call that the existing diffusion model. What they are doing is partial structure recovery. So it reads as follows. So if we denote the score error as E sigma as a difference between the score of our recovered distribution and the ground truth distribution, then if we have E sigma to be small o1, then as sigma goes to 0, the distribution converges weakly to P sigma. So in this case, we are successfully recovering P data. But however, if we have E sigma to the order of small o sigma to the -2, then we can show that the pi sigma concentrates on the manifold. So of the manifold density will quickly be diminishing as sigma goes to 0. So this is not yet the full story. We also provide a negative result that if our score is not so well as small o1, but omega 1, then it can recover arbitrary distribution on the manifold. So for any distribution on the manifold, we can construct such a pi sigma. So its score between the real score is of order omega 1, and it converges weakly to that distribution. So that we recover something that we cannot predict. So how this reflects what's happening in practice is that we believe the diffusion model, current diffusion model, operates on the median regime, because we see in practice that you cannot usually learn perfect score when sigma goes to 0 or at very score sigma, and it can actually diverge. And this regime allows it to even diverge. And in that regime, we can already recover the support on the manifold, so that we can already recover, like have very realistic images, the images people want. But however, we cannot have any guarantees for the distribution actually recovered on that support. So that is why we are saying that recovering the distribution is actually much harder. There's a rate separation than recovering the support, the manifold. And in practice, people might have only recovered the manifold. And to actually recover the density would be much harder. And apparently, existing empirical results does not indicate that. We don't have such a very accurate score function. So this is a negative result. And then we were wondering, inspired by this, can we do more? Like, even if given a bad score function, can we generate a distribution that's meaningful on the manifold? Because we have already seen that here the leading term is very clean, it's just the geometry term. Even if we discard the p data, the density information, we might also be able to do something meaningful. That is what we call the full structure recovery, the full geometry learning. That is, we propose a new algorithm that under this not well learned, badly learned score, we can still learn the manifold to be able to sample from the uniform distribution on the manifold. So suppose our score is not between the actual score with an error of small o sigma to beta for some beta greater than -2. So we are in the regime that diffusion model can only recover the support, the manifold. And then we propose the tempered Langevin algorithm that we multiply the score by a sigma to the power of alpha. And if we know what our score error is, we can select alpha, or we just make the alpha to be close to 0. And then the stationary distribution of this Langevin dynamics will converge weakly to the uniform distribution on the manifold as sigma goes to 0. So here this have quite some implications in we believe in many fields. Like for manifold learning, being able to do uniform distribution sampling indicates that we already fully learned the manifold. So we can approximate the Laplacian Beltrami operator on the manifold. And also this can be used for like solving PDEs on the manifold by Monte Carlo method, right? And for diffusion model, it can also lead us to sample from an unbiased distribution. So in many cases, people might not want to actually recover P data because your data sampled can have some bias, and you want to generate more diverse samples as much as possible. So this proposed an algorithm that allows us to do uniform sampling on the manifold. So here we advocate a paradigm shift for current diffusion models, that in existing diffusion model, we are trying to learn the target distribution. And we show that there's a rate separation that learning the target distribution is very difficult. You have to learn your score to be very accurate as small as 1, which is not the case in practice. You may put like much more effort to actually recover the target distribution. And if your score is not learned so well, you can only recover the support. However, if our target is to learn the geometry, to learn the manifold itself, we can allow for a much bad score function, and we still achieve this target. So it allows us to do uniform sampling on the manifold, and actually also some applications in Bayesian inverse problem with the uniform distribution as a prior. I should mention that we assume that the support is compact and connected, the manifold. So here's some numerical simulations on our theorem that we consider an ellipse, a 1D ellipse embedded in 2D, and then we use the same NERT score function to try to run a Langevin dynamics, try to recover the different goals. So for the left-hand side, we try to recover P data. As we can see here, it's very hard to recover P data. And even if we NERT the score, actually, this is a very toy setting, and we have already NERT the score for a sufficient long time, and it's still very hard to recover the P data. And in the right-hand side, if we just want to recover the uniform distribution with respect to the intrinsic measure on the manifold, then with the same score, we are able to do that. And this can be also plugged into the diffusion model by just one line of modification of existing diffusion model. So there's a popular framework in diffusion model that's called predictor-corrector framework. So in the reverse process, in each of the reverse step, we have an additional inner loop that runs this Langevin dynamics in this inner loop. That's called the corrector step, and it's widely used in diffusion models. And this corrector step tries to correct the distribution at that time to be more closely aligned with the distribution corresponds to the score function. And we propose to replace this Langevin dynamics by our tempered Langevin corrector to multiply the score function by a sigma to the power of alpha. Okay, the intuition here is that after multiplying sigma to the power of alpha, so the score function becomes a gradient of another score function, and that corresponds to a uniform sampling. So basically, the original, the leading term still preserves because we select alpha to be small, so that the original leading term still preserves, so that it can determine the manifold, the support of your limiting distribution. However, any side information about P data and also the learning error sigma to the power of beta, they become a small O1 term. So it does not contribute to the final limiting distribution. So basically, now the drift here is approximately the perfect score for the uniform distribution, for the distribution that is a uniform distribution on the manifold convolve with a Gaussian distribution. So that is the reason why we can, as sigma goes to 0, we can recover this uniform distribution. So this idea can be also applied to the guided setting. So in addition to the score function we can also have a guidance function that guide to have a tilted distribution on the manifold according to our guidance. So we show here that run this tempered Langevin dynamics with guidance minus gradient V, and the stationary distribution converges to a distribution that's proportional to exponential of minus V on the manifold. So there's no prior information on the data distribution, how the data is generated. It's purely on your guidance. So in this case, we also run some experiments on real-world diffusion models. We use Stable Diffusion 1.5, and then using our tempered Langevin dynamics. As we can show that both the image quality and the image diversity can be improved using our framework. So here's the two score. One is the image quality, how realistic it is according to your given prompt. And the diversity score, that is how diverse our generated image is. So here is some generated images. That the first row represents to an original predictor corrector framework. And then the second row is the predictor with corrector being our tempered version. And we can see that the images are more realistic and also contains more details in it. So in conclusion, we have that under the manifold hypothesis, we analyze score learning and show that score learning learns the structure first before the distribution. So in this case, it implies that in current diffusion model or score learning, people might not have learned the actual distribution, but only recovered part of the structure, only the support of your manifold. And also, this inspired us to design a new algorithm that targets to learn this full distribution of full manifold, that is a uniform distribution on the manifold. And however, there are some limitations and potential future works of this work. So the first is that there are some technical assumptions that we believe can be relaxed. So currently, we in our theorem, we assume that the score is not very well or badly, but by the L infinity norm. So a more realistic scenario is that whether this can be relaxed to L2 norm, because in actual score learning or diffusion model training, we're learning it with L2 norm, not the pointer-wisely learn the score very well. And also the statistical complexity. So how many samples are needed to actually recover the manifold, and how many samples are needed to recover the actual density. It's also missing in this work. And what we do is a asymptotic analysis on the score function without these statistical complexities. Also, our analysis is fully on the discrete time, and fully on the continuous time. And in practice, to do sampling, people will first discretize your dynamics, right? And we think discrete time analysis would also be an interesting future work. Yeah, thank you very much. And that is all about my talk. And you're welcome to have any questions.